Up until this point, we've only been looking at equations. But what if one side is not equivalent to the other side? We have an inequality as opposed to an equation. For example, 2x minus 5 is greater than 10. Well, generally we solve this the same way we would an equation. I'm going to add 5 to both sides to get rid of the minus 5 on the same side as my x, leaving me 2x is greater than 10 plus 5, which is 15. Okay? And then I would divide through by 2, the coefficient of x on both sides, to get rid of that and isolate my x, which is greater than 15 halves or 7.5. Okay, that's pretty easy. Our inequalities so far look like they are the same as solving equations. But wait a second, there's one major difference you need to be aware of for the exam. What if I had the following inequality, 5 minus 2x is greater than 10, and I began solving it much the same way. Subtract 5 from both sides. I'll get minus 2x is greater than 10 minus 5, which is 5. And I'll divide through by the coefficient of x, which is minus 2 in this case. And that isolates my x. But the key for an inequality is I must switch the direction of the inequality. X is now less than minus 5 halves. So when we multiply or divide by a negative, we must switch the direction of the inequality. That's one key difference between inequalities and equations. Many of you might know that already, but it's so important it's worth emphasizing again. Likewise, if we take the reciprocal of both sides of an inequality, you must switch the direction of the inequality. That's one students don't appreciate in most cases. So how do we show that? Like, why is that really the case? Well, I could solve this a different way. I didn't have to divide by the coefficient. I could have just added 2x to both sides. I would have gone 5 is greater than 10 plus 2x. And then I would subtract a 10 from both sides. 5 minus 10, which is minus 5, is greater than or equal to 2x. And then I divide by 2, no problem, because I'm not dividing or multiplying both sides by a negative. And simply x is less than minus 5 halves. This is the same as this. X is less than minus 5 halves. Here I solved it a different way without dividing by negative. So if I did not switch the direction of my inequality when I divided by negative on both sides, I would have been wrong. Let's extend our discussion of inequalities to compound inequalities, which you're more likely to see on the exam. In this case, I've got 2x minus 6 is less than 10, and 2x minus 6 is greater than negative 2. I have two inequalities connected by an and condition, which means both parts have to be true. Alternatively, I've got two inequalities connected by an or condition, which means one part has to be true only for the whole statement to be true. So let's take a look at these. We can always solve our compound inequalities as separate inequalities if we choose to, whether it's an and or statement. So let's go ahead and do that in this case. 2x minus 6 is less than 10. That means 2x is less than 10 plus 6 or 16. Divide through by 2. X is less than 8. On the second one, 2x minus 6 is greater than negative 2. So add 6 to both sides. 2x is greater than plus 4. Okay, divide through by 2. X is greater than 2. These are my two solutions. X is less than 8 and x is greater than 2. Note, I can combine these with my and condition into one essentially three-way inequality. X is less than 8 and greater than 2. You'll often see this the case. I have a three-way inequality, okay? And by the way, we can graph that too on a number line. That would look something like at 8 and at 2. We know x is between 2 and 8. So it's greater than 2. We use the open circle to indicate everything to the right greater than, but not 2 itself. An open circle at 8 to indicate it's less than 8, so everything to the left on the number line, but not including 8. Okay? This is an interesting one because we could have actually solved this as one compound inequality in our format that we have right here. So what would that have looked like? For example, we could have set up 2x minus 6 is less than 10, and is greater than -2. And I could have gone ahead and kind of solved it as a three-way inequality with my linear expression, one variable, in the middle. I would have added 6 to both sides, so we're less than 16, 2x, and greater than, adding 6 to both sides, 4, and I would have divided by 2 and figured x is less than 8 and greater than 2. The same answer we get above, okay? Let's try this out on the OR condition. If I solve the OR condition, again, I can always solve it as two separate inequalities. So that's 2x. I'm going to add 6 to both sides. 2x is greater than 16. Very similar to our last one because they are, in fact, the same inequalities, or nearly the same inequality statements. And then I'll divide through by 2 on both sides. X is greater than 8. That's one solution for the first inequality. How about the second inequality? 2x minus 6 is less than or equal to -2. Add 6 to both sides. 2x is less than or equal to plus 4. Divide through by 2 again. X is less than or equal to 2. That's the solution for my second inequality. So these are my two solutions. What would that look like if I graphed that? That would be something like, again, I've got these points 2 and 8. And the first one, x is greater than 8. So I'd have an open circle at 8 and greater than. It's everything to the right of 8, but not including 8. X is less than or equal to -2. So in this case, I have an equal condition as well. Notice the less than or equal. In that case, I used a closed circle to indicate 2 is part of my solution set, and it's less than. It's everything to the left on the number line represents less than. Don't make that mistake. Sometimes students think -8 is greater than -6. No, it's not. It's to the left on the number line, therefore it's less, okay? So this is what our graph looks like. Well, wait a second. This is very different than the graph we saw in the AND condition case, which looks like our typical sort of dumbbell, if you ever use that on weights. On the other hand, the OR condition generally graphs to an open in the middle. And why is that in the ends? Well, let's think about that. In my solution set, I'm essentially saying something to the right of 8, let's call it 10, is a solution. But it's not an AND condition, it's an OR condition. So I'm either 10 or I'm something to the left of 2, which might be, say, 0, right? I only have to meet one condition. If I had an AND condition on this graph with this inequality, the solution set would be no real solutions because there's no way I can be 10 and be less than 2 or be 0 and be greater than 8. So we can see the OR condition has this type of graph and looks a little differently. By the way, I cannot generally write this out as a three-way inequality like we do before. But nonetheless, we can solve our AND conditions, OR conditions, and graph them.